Today, I want to talk about a brief um, aside work that I am doing in my current research and PhD work, which is the analysis of how to model multi-agent processes. So here I will try to introduce basically what is for me a multi-agent system and more generally speaking, a complex process. Then I will try to detail the mathematical model that I propose to describe a one-dimensional uh, model of n robots, n mobile robots. Then I will discuss a little bit about how to analyze the stability of this mathematical model, how to design the controls that drive these robots, and show some of the results that I have got so far. Then I will detail a little bit about the future work that I will try to achieve maybe in the next years. Okay, so basically I am interested in complex processes. So basically a complex process in general is a system which that is formed with many components, and the interactions between the components are highly nonlinear usually. But then it's difficult also to model them because of that, because how complicated interactions between these elements are. So examples of complex systems are what we can see actually nowadays in the Internet of Things, what can be seen in flocking or in groups of robots. So when I talk about a group of robots, we usually call them multi-agent systems. Every agent is a robot in the process. So this example in the figure, if we see a figure, it's just an example of a multi-agent system where we have a robotic formation in the shape of a ring. So in this case, we can maybe try to figure out how to control them so that they achieve a certain formation, there are certain interactions that they have to accomplish between them, and so on. So the problem with trying to control a multi-agent process is that usually, as I said before, the mathematical model of the whole formation is difficult. So if I try to figure out ways to simplify the mathematical model of this type of robotic formations, it will be wonderful. And also, if I get simpler models, it means I can design a control law simpler as well. So basically, what I'm proposing here is to study this formation, but since starting from a very simple case where they move only in one dimension, they move unidirectionally speaking in maybe the dimension of x, which is the distance or something. So basically, what I'm saying is that you can model them as particles, but also what I'm all interested in modeling is the interaction between them. So I may be able to model not just the process, because this is a very naive maybe simplification of the mobile robot, but it's because I'm more concerned about what is the control law that drives each robot. So let's say that we have two robots and we need to keep them within a decided distance between each other. So you create some sort of operator over the error, computing and evaluating the distance between them, and that's going to create some forces that will attract them or will repel them. So if we say we have a simple PD controller, we can say then that maybe we have something like a spring in a damper in parallel connecting the robots. And that's actually the mechanical intuition of what is happening when you add a control, a simple PD control. But what if if the robots have some issues, like they can only see what is in front of them, but they cannot see what is behind them? Then I have to impose certain constraints. For example, if the robot M1 can only see the robot M2, but M2 cannot see the robot M1, then it means that F2 is equal to 0, and that creates a different mathematical model for the whole system. So what I'm saying is that basically in this analysis, I'm trying to show something like this. This was a project created by some students that I was supervising for digital control engineering. So they created a simple PD control or PID control to maintain the mobile robot within a decided position of something that is in front of them. So if we analyze this simple robot, this can see what is in front of it, but not what is behind of it. And the idea is that I can generalize the mathematical model of using this simple rule, that the robot can see only what is in front of it, but not what is behind of it, and it's moving in one dimension, to create a generalized model for N robots. Okay. So, and the good thing about this generalized model is that it's linear. So you may have something like this, which is adding several robots in a ring formation, right, to try to keep them in a desired distance. Okay, so this is the general mathematical model that I present in the article, and the idea is that you can now analyze a system as any linear system using any stability analysis tool, and idea that I think there's plenty of them for linear systems. So I can decide, well, we have this output. The output is the measurement of the position of each robot. If we have maybe 3 robots, and I may find a MIMO system, and I can analyze how to design the gains of the controller for the control gains, sorry, for each control in each robot. So I did that by minimizing a cost function. That cost function is just the root mean square derivation, which is the subtraction between what I desire minus what I am measuring. And I do that by using a simple evolutionary algorithm. It gives me the set of control gains that I should use in every robot. And as I can show here, if I use this algorithm, it gives me some set of gains that I can use so that deformation every robot keeps a desired distance between each other, having some initial condition, right? So here is another result. I may also do some tracking by changing what my decided position as something that is varying over time. And well, that's basically it. I think I was almost running out of time, sorry. Then the future work is I'm looking to generalize this mathematical model into a 2-dimensional model. Usually what I have is a Laplacian matrix, of course, that tells you the interactions between the robots, and then you can design a controller by using this Laplacian matrix. But the idea of this work was to try to look at it in a different way by using some sort of mechanical intuition, right? And also, the good thing about this is that I may try different low-order controllers. Instead of just a PD controller, I may try something different. And the optimization function can vary, can be whatever you may like. I'm thinking maybe an LQR cost function. And also, actually, the first reason why I did this was not because of trying to analyze multi-agent systems or robotic formations, but I was trying to use some information theory tools to this kind of systems. So I think that information theory can be applied in this kind of projects based on some previous results that we have already published just recently, which are these 2 over here. So I hope this was clear enough. Thank you very much for the time, and I'm here to answer any questions you may have. Thank you. Thank you again.